So now we're going to take a look at a variant of what we just described before. This is called applyAllSplitIndex. And you'll see in a second why this one is given that particular name. And let's start by just recapping the point of this method. It should be no surprise at this stage. This method takes a list, it takes an op, and it takes a fork join pool. And the op is a function, and we're going to apply that function to every element in the list and do the computations of the fork join pool. All right, so that's big picture view, no surprise, no change. The implementation, however, is quite a bit different. And it's really quite fascinating. So the first thing we're going to do is we're going to do this completely insane trick that is due to the semantics of generics in Java, which is bizarre to say the least. What we're going to do is we're going to create an array of t. So remember, this is a list of t. We're taking a list of t. We create an array of t called results. And we're going to go ahead and make that array be as big as the size of the list. And don't even get me started on what this means. We're using Java reflection in order to be able to create a new array. And the type of the array is the class of the item in the array. And the size of the array will be the size of the list. So now we have a new array. And we're going to use this in a very cool way. Notice that this array is local to the applyAllSplitIndex method, but it's going to be global to the nested class called splitter task. And this splitter task is a little different from the previous splitter task in that it extends recursive action rather than extending recursive task. But it's going to play a similar role, but it's going to do it in a different way. And the different way is all intended to avoid having to do data copying. Although you'll see that it's not quite as cool as we might want. And you'll see how that works in a second. But there's another alternative too, I'll show you. So then what we're going to do is we're going to go ahead and invoke the new splitter task in the fork join pool, except this splitter task is now going to start at the 0th location and go to the end of the list. So what we're doing is we're passing in indices. Remember before we passed a list in to splitter task. This splitter task has a different structure, and instead of storing a list, it's going to store indices to the beginning and one past the end of that sublist. And of course, what it's going to be pointing to is it's going to be pointing to this array. And we'll talk about that in a second. And then when we're all done with the invoke, remember invoke, as always, is a two-way call. When invoke is finished, we're going to take the results, which is this thing, which is this array, and we're going to convert it back into a list. And so that list will then be passed back as the return value. Now, as you'll see, that's really pretty cool. But it does have one downside. We have to convert the list into an array, and then we have to convert it back again into a list, which ends up incurring extra overhead. So if you don't want to incur this overhead, a much cleaner way to do things is to change the signature of applyAllSplitIndex to take a results array. So remember before, we returned the list as the result. In this approach, what we can do is we can pass in an initialized array, and the results will be put into that array. And then we'll get it back when the call returns, and we don't have to do all these conversions. So it's cleaner. We don't have this bizarre Java reflection trick, and we don't have to do the conversion back. So this approach would arguably be a little cleaner, but we didn't have to change the signature of the method, so that might not be a good thing. Okay, so let's take a look at splitter task. So in this approach, splitter task is a recursive action, not a recursive task. But it's similar in other ways in that it's going to split the input up into two chunks, and then recursively split those up into two chunks, and then recursively split those into two chunks. So it'll split, split, split in a nice balanced, even binary tree of splits. And here's the constructor. You can see it takes low and high, and it stashes those things into private fields. So here's the compute method. Compute is going to recursively perform the computations in parallel, as we did before, but the implementation is just ever so different and arguably ever so more efficient. First thing we're going to do is we're going to, once again, figure out the midpoint in the current range. This is a little trick you've probably seen that done before. So we take the high plus the low, and then we divide by 2, or we right shift by 1, same difference. And so we end up with a midpoint, and that way we can split the list evenly in half and efficiently in half. It evenly and efficiently and recursively partitions the list. The first thing we do here is we handle the basis case. So this is the base case for the recursion. If mlow equal mid, we only have one element. And so in that case, we go ahead and we'll do the following. Notice results is that array we created that's actually up here. It's internal to applyAllSplitIndex, but it's global to this nested class. So we're going to say the results sub mlow is going to be set equal to applying the operation to the list element at mlow. So list element mlow, we're going to go ahead and apply that operation and store it into results mlow. And if it's not equal to mid, in other words, there's more than one element in this thing, what we're going to go, in that case, do is we're going to create a new splitter task, this thing, and we're going to have it work on the range from mlow to mid. So we're going to copy mlow here, then we're going to update mlow, and mid. This will be the left-hand side, the left-hand fork join task. And we're going to go ahead and fork that guy. So that's going to be forked. That will then be arranged to run asynchronously by a thread in the worker thread pool through a little work stealing, most likely. And then we're going to go ahead and compute in the current parent thread. So the same thread that called compute up here calls compute here, except now we've just gone ahead and updated mlow to handle the right-hand side. So we're going to compute the right-hand side in parallel with the left-hand side. And then when we're done with calling compute, we'll call join. Now, join is interesting because notice that join doesn't get a result back. Because of the fact that we used recursive action rather than recursive task, lt.join doesn't have a return value. It only has something called a synchronization point. And that's just a fancy way of saying that the memory is properly flushed so that when you join with something, you get back consistent results, despite the fact that this processing was actually done in a different thread, probably running on a different core. And we don't have to get a result back because everything is done in place in the results array. This implementation is also harder to program and understand since it's, number one, recursive, and since it's got this super clever results array that we're storing the results into. So it's even a little bit more complicated, although as we'll see, it's likely to be more efficient because it's not doing the copying that the other one was. Although we'll see that there's pros and cons there. So let's take a look at how this looks visually. So once again, here's the initial foray into this. We say fjpool.invoke, create a new splitter task, put the task in the queue, the shared queue. This, of course, is a non-fork join client, uses invoke to insert the starting point task, which, as you can see, straddles the entire range of the list from 0 to size. And then everything else looks pretty much the same as applyAllSplit. The difference being that this approach doesn't have to do all those sublist copies. Now, if you use the version I show you here, it does have to do the final copy at the end to copy from the array back to the list. But if you use that other approach that we looked at, it wouldn't even have to do that. But that would change the interface a little bit. So work stealing overhead will be low, just like with applyAllSplit, because we're recursively partitioning things rather than throwing everything into a single worker thread's DAC. We're going to recursively decompose these things across multiple threads, which will get a balanced tree of results. There still will be some extra method calls because, of course, it's recursive, but that's probably not very significant on modern processors. And again, fork and compute should run in parallel in most circumstances. And join returns no value and just serves as a synchronization point. And the other nice thing about this is there's a nice balanced tree of join calls, so that's also going to be more efficient than the original applyAllItter solution. Okay, so that's an overview of applyAllSplitIndex.